place where it might be, as long as you look in a place that it might be, you're going to find it because it's going to be put in every place that it might be instead of putting it in one place. So notice the trade-off. With one approach, you have to sort multiple places because it's only going to be in one of those places. But it might be in any one. Whereas with the R plus approach, you're going to see about putting it in multiple places, and you can search in any one of the places it might be because it's always going to be that question.
So if you're already putting things in multiple places, wouldn't it be easier just to make a grid so everything's, got a set boxes, like a set size, so you don't have to care what the box is. You just have to know, oh, it's in a Z, basically.
Yeah, you certainly can take approaches that are based on grids, although some of the grids might end up being wasteful because there might not be all that many things inside them. If you have things that are dense, then some kind of approach that's based on a grid, and that maybe hashing based on the grid might be a very interesting thing to go ahead and do. If the thing isn't dense, that might not be bad. Let me put it this way. I love the question because it means that you're thinking about alternatives. And this isn't the only approach. It's not even the main approach that's used anymore. It simply is a good approach to think about and then say, but I think I can do better for the environment I'm working with, not only for the application I'm working with, but the data that I'm working with. So yeah, I mean, I began by saying question authority, which I suppose in this case is me. Thank you for, thank you for doing so. There are all sorts of variations. Well, here the authority is saying question authority, so I think you have to question me by following all my directions, because I'm telling you to question the directions. But seriously, I mean, it's great to look at alternatives. And again, there's no one size fits all. There are lots of different approaches for different environments. But how much code do you want to be able to maintain, over time, and variations, multiple threads, things end up breaking when you have too many variations. So what is deletion? It basically means search for the entry to be deleted and remove it. In the original R tree, it's something where it's only going to be in one place, so you only have to remove it from one place. And of course, what do you do if you have an underflow? If a node becomes full, it may mean that you have to end up, see what you can do about taking the remaining entries and reinsert, and you may have to do merges on that and all the rest of it. And as I mentioned at the beginning, and I'm not going to prove this, for one thing, I don't know the detailed proof, but some of it comes from experimentation. It works really well on 2D. It works well on 3D. Doesn't work nearly as well as on four-dimensional more, and there are other variations of it. As mentioned, you can work with other things other than rectangles with the convex polygons. So high-dimensional data sets typically end up being collections of points rather than regions. There are very few four-dimensional maps that are out there. I suppose you can have X, Y, Z in time if you really insist, but as far as I know, there isn't that much that's been done with four-dimensional mapping in regions and so on that are there. And again, there are, a typical thing would be find the nearest neighbor to a point. In other words, you have some characteristics of a person. Who are the neighbors who are nearest to that person? You've got 12 characteristics of the person. Who are the people who are most similar to that person? And that's there. And the R tree ends up becoming worse as you get to higher dimensions and so on. And so there are variations of nearest neighbor. Even the notion of what constitutes nearest neighbor ends up being interesting. But again, there are lots of apps where variations of this end up being important. I'm not going to go into the detailed techniques that are used in that, but variations of this end up being really important. And so we have spatial data management with lots of different applications. And again, I've been talking about overlap, but you can also deal with the containment issue. How many things are within this entirely? And there are all sorts of other variations. Is there an intersection with everything inside? All sorts of different things exist. Our tree was widely used in geographical information systems. There are 17, this is a list of things. There are lots and lots and lots and lots and lots of other things that end up being used. The main thing you should get from this, and again, it's not in the final, is that the B tree is really nice, including for multi-dimensions. It doesn't deal with the problems that you have in this space well. Another solution was needed. So all that is there. And that, with about a few minutes to go, which means I can end up starting on the LSM tree thing, and both of these are posted. But before I do that, are there any questions that people would like to ask that I'm willing to answer? No, I will not tell you how many questions there are on the final, assuming I remember, because that would be a useless piece of information to give you, because I've been known to have multiple part questions, and the difficulty of the individual parts ends up being, more interesting than the number of parts that are involved. Let me just switch over to the other window in case I actually have time to do it, and then we can see about answering questions.
So what's the name of a couple of algorithms that are able to handle a high amount of dimensional data?
Let me see what I can do about sending you some examples, because frankly it depends on the applications. There are all sorts of different things that are used in recommendation systems and different things that are used in machine learning and so on. I'll say right off, I am not an expert in this field. I know a little bit about database. I tend not to know that much about the multi-dimensional feature analysis approaches. I will give you one, because it's one that almost was something that I have as extra slides for 180, and I can even end up bringing up the slides. There's something which is called data mining, and there are courses here in data mining. It's a very interesting field, and I'll just mention one of the techniques that's used. As part of what you're doing is you're looking for clusters of data. You're looking for things where there's a whole bunch of different points that are in this region, and you've got a multi-dimensional region. Okay, so here's what you do. You start off with, again, a multi-dimensional cube, a 17-dimensional cube. Don't ask me to draw. Buckaroo Banzai and the seventh. What was the dimension? If you haven't seen Buckaroo Banzai, strange movie, interesting cast. Anyway, so you have a 17-dimensional cube, and you chop that up into pieces. And so you end up chopping it up into a number of pieces in all 17 dimensions. So suppose that you have 1 million points in all of them, and suppose you chop it up into k different pieces. Some of those pieces will have a lot more points in them than other pieces. The ones that have a lot of points in them may be places where you end up having clusters. The ones that have few points in them are not going to have clusters, right? There's a lot of things inside. So you take the ones that have a lot of points inside them, and you recursively do the same darn thing. Lather, rinse, repeat. You go ahead and you chop those up into pieces, because they might still be pretty big, and you see which of those pieces have things inside them. And then, as you get something small enough, you find something which is small enough for you to talk about, where there's a cluster or multiple clusters of things that exist inside that region. But you might tell me, I'm glad you asked, that the way that I did the chopping is, it might be something that there was a big cluster, but I ended up chopping it so that big cluster ended up being chopped into so many different multi-dimensional pieces I didn't find it. Well, lather, rinse, repeat again. Chop it up again, but using different boundaries. Chop it again by using different boundaries. Randomly go ahead and pick how you do the boundaries using 100 different approaches with different boundaries. And so when you're doing this with reasonable random numbers, you're going to find clusters reasonably well and moderately quickly. But you also have to have a way of being able to figure out quickly, how many points there are in the cluster, and there are reasonable data structures for doing that and all the rest of it. So that's an example of something that has been commonly used for finding clusters. And again, it's part of the field of data mining. And there are lots of other techniques inside the area. That's one that I can, easily talk about, which I know something about. One of the earliest approaches. There was a phrase that was used at one point of a data jail. It's ancient, it's not used anymore, where there was so much data that you didn't understand what the heck you had, because you had no way of analyzing it. This is one of the early techniques for viewing what again became to be called data mining. It actually was originated by a fellow by the name of Rakesh Agrawal, who was at the time at IBM Almaden Research. And again, it's an extremely common technique. He then joined Microsoft Research for a while, and now has his own company doing work that ends up being related to this and other things. Other questions? Yep.
Is the final going to be the full 3 hours?
Yep.
Okay.
Well, for those who want it. I'm not going to force you to stay any longer than you need to. But the full 3 hours will be available to you by the time you hit 7 o'clock I'm sure you will be happy to be able to finish up with this stuff. If there aren't any other questions, I will spend a little bit of time telling you a little bit more about log-structured merge trees. The thing is that we're talking log-structured merge trees, although they go back about 20 years, they become very, very popular when people realized, and some of this started off with Google. Google, well, as something that they had public, but they had done variations of this before they made it public. They have a system called LevelDB, which is based on log-structured merge trees, which again, they use in practice inside Google. They use variations in practice. And then Facebook came up with something which is even more popular, which is called RocksDB. And there are lots of good papers about both of these, which again, both of them are open source. And RocksDB is now quite a bit more popular than LevelDB. And they're all based on the notions of a log-structured merge tree. So here we're talking about something which is moderately recent, meaning it was 20 years old, but it didn't end up getting a whole lot of popularity until a lot of the big data applications caused it to become much, much more popular. Not going to go through the notable notes other than, again, encourage you, whatever you want to say about me, please. Saloni deserves a huge amount of praise for doing really great work 3 times and not getting overdosed by the puns, even though she's had to deal with them 3 times. These are slides. A friend of mine by the name of Jun7, who at the time was working at a company where I also consulted called Logic Blocks, did it when he was there. He got his PhD from out of CMU with a professor by the name of Anastasia Alamaki, who's been teaching now for a number of years at EPFL in Switzerland, and she's had a bunch of really, really strong students. Logic Blocks ended up being bought. Ryan is now working at Amazon Web Services, and he does absolutely terrific work, plus he's an incredibly nice guy as well. So again, in the I/O approach, you have things inside the RAM, you're transferring, you're trying to minimize the block transfers from disk. And the assumption is that you've got a large main memory, fast CPU. Again, I will remind you about NUMA. This is not a class about NUMA, but remember that your locality matters. And I didn't mention this before, I will just mention it right now. I talked about L1, L2, L3 caches, where L1 is on the core and L2 would be associated with the CPU, and L3 would be on the board and all the rest of that stuff. There are different levels, and I'm not the expert on hardware. But remember that locality is king. Locality matters like crazy. And you should really, if you haven't taken a hardware course, and if you're not done, take a hardware course. NUMA just ends up being really critical to understanding performance. But there is this notion of write amplification, because not all writes are created equal. And so the idea is that if what you're trying to do is to deal with sorting an array and then searching, going ahead and searching it, and you're trying to go ahead and do a scan, then you basically have whatever your block size is. It's still going to be order n, even when you have a given number of blocks. And if you're doing a search, then again, or you're doing an insert, there's no benefit either in doing the queries or the inserts from what your value of B dealing with the block size. And let's look at B trees. So you've been referred to one of the early B tree papers by Douglas Comer. Not sure if he was the originator of the B tree. It was called the ubiquitous B tree. And basically, you have this notion that you end up having something where you have, you get told, we've got the traffic cops who tell us about the subtrees. And here, we're just fitting, 2 kids inside, so it happens to be a binary tree, but in practice, as we know, you have the things with the traffic cops and the values, and you can fit a lot more than 2 there. And everything gets stored inside the leaf, so the data is there. And basically, if everything is warm and all your data is in memory, then it's going to be constant time, meaning in terms of the disk IOs. And in the worst case, in case things are cold and you don't have your tree inside memory, then it's going to be just log in to be able to go ahead and do the search. And the nice thing is that Again, by having a bigger value of B, you end up having to transfer more data, but you don't have to do as many seeks if you're going out to the disk or SSD to be able to end up getting the data. Okay? Again, because you end up having the value of B, it basically ends up improving things by what effectively is log to the base 2 of B. So it ends up being a better thing than searching the array. Basically, here you're going with log to the base B, whereas with the array with binary search you do log to the base 2. So log to the base B is better than log to the base 2 of n. So it's just an use here. It's log to the base B of n divided by log to the base 2 of n. But let's see what happens when you have updates. Okay, and you could end up, in the case where you end up having 5 updates being done at the red nodes, there could be a lot of splits. Let's say that these are inserts. There could be a bunch of splits that happen. It could mean you could have a situation in which you end up, if you're lucky, then only the red nodes have to be touched. So you end up dirtying those 5 pages. That ends up being good, right? That's nice. But the trouble is that you could have a situation in which you end up having to dirty a lot of different pages. You could end up dirtying things all the way up the paths inside the tree. There could have to be 17 updates, and that ends up being relatively expensive. Again, I'm going to skip past all the variations, and so not get into that because I only have about 5 to 10 minutes. But basically, again, as I indicated, you could have things where when you're doing this, you're writing the 5 red pages that are leaves, you could have to dirty everything inside that tree. And that ends up being expensive, because writes tend to be fairly expensive. So basically, the trouble is what's called write amplification. I mentioned this already earlier. What does write amplification mean? You're only writing 1 leaf page. You think there are only 5 writes, but each write got turned into a whole bunch of different writes. So that's expensive. If you maintain life as a heap and you only append at the end of the heap, then life is easy. Of course, searching becomes more expensive to be able to do that. So again, you have to deal with what the implications are of that. And so there is a notion of a log structured merge tree. There are also some things that are called B epsilon trees that are kind of nice. And by the way, the reason that Ryan was talking about this, and he does have a publication on this, I believe finally, he ended up while at Logic Blocks implementing a variation of B epsilon trees called the alpha trees that was really, really nice. So he wasn't just talking about this abstractly, he was building his own variation of it. And the idea is we're going to have multiple layers of the data structure, and you're going to put the updates into the smallest data that they fit in. When you do a delete, you're going to have tombstones. You can have a record that says this data isn't sleeping, this data is dead. If you know Monty Python and the Dead Parrot, if you don't, it's all right. Just marking data as being dead. You always write into the top layers of the tree, which are moderately small. And you know what happens when the top layer is filled? You move them down to a lower layer of the tree. And then when that becomes full, you move things down to the next lower layer of that tree. And you can garbage collect as you go ahead and do it. And there are variations of it. But the general idea is you're only going to write in one place. You're only going to write in one place. And so the overlay size layers can end up spilling to other layers. Okay? And so, basically we're going to deal with amortization of things when we need to write to lower layers, because we're going to be writing things involving a whole bunch of data to the next lower layer. When we have to write to a lower layer, we'll write 50 things to the next lower layer, as opposed to having to do writes for every single item. We're going to have things with a whole bunch of items that end up moving down. So here's an example. We have a database size which is 100 million items. Let's assume that we can have 3,000 items on a page. And we're going to have layers. And sometimes, in fact, when I first described this, I said assume each layer was 10 times bigger than the other. Let's assume that each layer is 50 times bigger than the one below it. We have a layer of a given size, and now a layer that can have 50 times as many items. That would be 150K items, 50 pages worth. and the next thing can have 50 times that, which is 7.5 million or 2,500 pages, and the next one 375 items, which is 125K pages. And now we get a picture. So what you're writing to is something which is inside memory, which might end up being a page, and you'll also be dealing with a log because you want persistence. So you'll also be writing things to a log. But you've got this thing that is inside memory, and behold, ate too much, you're now full. L0 is now full. What do? You end up spilling this thing over to L1. Okay? And basically, you ended up having only to write once to L1, even though there were 60 different things that you put inside this page. So basically, the per item cost was 1 plus 1/60th. There is going to be other spilling that can happen, but you're amortizing a lot like the box scoring or group commit kind of thing that we talked about. You're not writing out L1 for every one of the items. You're writing only when this became full, and now it's no longer full, so you've got a lot more space up here that you can fill up. Somebody's bound to go ahead and throw something at me, which is how do you do searches? I'll give you the basic idea. You may have to search inside multiple different levels, but you're going to keep each level organized well. So when I write it out to L1, I'll go ahead and I'll see about making sure that the thing is sorted inside L1. So that's going to end up being done. And when L0 becomes full again, I'll write it out to L1 and I'll merge. And I'll garbage collect. Because it could be that the same values are getting updated lots of times. Unless I need to keep snapshots around, I can get rid of old items that are out there. And since I am out of time, I will mention one other technique. Do you remember our good friends Bloom filters that we talked about when we were talking about distributed database? Some of you may, some of you may not. What you can do is, you can keep track of a hash table with bits in it for every value that appears at a given level. Because we're going to be doing the same thing. As L1 fills, we're going to move it into L2. As L2 fills, we're going to move it to L3. Let's say we have L0, L1, L2, L3. And we're looking for, somebody who's named, Alexander Wolf, who's the dean around here. And I'm looking for Alexander Wolf, and I have a Bloom filter that for each name fills in a 128-bit vector if that name appears in L2. I'll have that for L, I won't bother having it for L0, which is in memory, but for L1, L2, L3, I'll have a bit vector which says, is this value existing at this level? And so if I'm looking for Alexander Wolf, I'll see he's not in L0. I'll see that he's not in L1. I'll see that he might be in L2. Remember, it's a hash, so he might end up being there. If I look inside L2 and I find him, then I have found him. Do I look at L3? No, L3 is older data than L2. L2 is more modern data. L2 will have the current value. No need to look inside L3, even if I haven't garbage collected from the lower level. And if he's not in L2, even though the bit was on, then I'll search in L3. So the general idea is that this is very much write optimized. And it works pretty well when it comes to read, because you can do tricks. There are other variations, like that Bloom filter thing that I just mentioned. You can see, remember, with the Bloom filter, you will get no false negatives. You might get false positives, but by having, again, a moderate-sized hash table, you'll generally get pretty good things. So you won't be that many false negatives to work with the searching. The general principle, which is why I wanted to talk about these two things at the end, is we've talked about a whole bunch of different things in this class. 1,000 flowers have bloomed all over the place. There are many, 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 many different variations of this that exist. Invent others. Ask questions about particular data structures that are useful for that problem. Don't start off with something which says, this is what I taught, therefore it's right. This is what you were taught, so maybe it was right for one particular application or one particular assumption about hardware, for one particular assumption about data 30 years ago. Question authority. Better yet, become the authority for things that apply to what you're trying to do. Anyway, a lot of stuff in this course, as you've discovered, as you've been studying for the final, it doesn't tell you everything you need to know database, but there are principles that you get to figure out where to apply appropriately and where to question. Thanks, and see you on Wednesday.
Thank you.